material as well, base sizes, permutation groups. Thank you.
Thank you very much. And thank you very much for inviting me to speak here. So, as you may have surmised from my title and from Joanna's very nice plug, my talk can kind of be considered a follow-on from Joanna's. I'll be talking about what I've been doing in my PhD with Martin Liebeck over the past 3.5 odd years. So, in particular, my work is a contribution to the base size 2 project. So, to classify all finite primitive groups, primitive permutation groups H with base size 2. Okay. Now, in this talk, I'll be focusing on affine type groups, which we can write H equals GV. My notation's a bit inconsistent with Joanna's, but it's the same thing, where the point stabilizer here, G, is almost quasi-simple. Well, Joanna told us a bit about quasi-simple groups. So what's an almost quasi-simple group? Well, we say that a group is almost quasi-simple if it has a unique self-centralizing quasi-simple normal subgroup, which I'm going to denote by this E of G here, okay? Or a slightly easier way to think about them is that if you take your group and you quotient out the center, then you get an almost simple group, okay? In my work, I also add an extra restriction, which is that when I take my irreducible module V and I restrict it to this quasi-simple normal subgroup here, I'm going to, this restriction will be absolutely irreducible. So if I extend the field, then the module remains irreducible. Alrighty then. Well, so Joanna told us that if we've got a group of affine type with base size 2, then that means that's if and only if G has a regular orbit on V. Because obviously, as I just said, and as Joanna said, the point stabilizer is just our G here. Okay, so then my aim is to classify pairs G and V, where G has the properties I just described, so it's almost quasi-simple, and it has this quasi-simple normal subgroup, where G has a regular orbit on V. Okay? So Joanna, although she was talking about mainly just quasi-simple groups, we also have a complete classification for many of the cases here where I'm talking about almost quasi-simple groups. So again, when we have an alternating group, when the socle of G modulo, etc., is an alternating group, we've got a classification there. And also if it's a sporadic group. Again, if we've got a group of Lie type where the size of G and the size of V are coprime, then that's done as well, and it was done by Kohler and Parlings, based in their work trying to prove a section of the KGV problem, and their work relied on some work of Goodwin and Liebeck. So really, the case that I'm looking at is where we've got a group of Lie type where the size of G and the size of V are not coprime. Okay? Now, as you might imagine, the analysis of this particular case splits in very naturally into 2 different cases. The first is where the finite field of the vector space and the finite field associated to the group have the same characteristics. That's our defining characteristic case. And if they have different characteristics, then we're in the cross-characteristic case. So for the majority of my talk, I'll be talking about the cross-characteristic case, because I've actually completely finished with that. Okay, and then towards the end, I'll be telling you a little bit about my work in the defining characteristic case. Okay, right, so here's my result. So if I've got one of these almost quasi-simple groups G with an absolutely irreducible restriction to this E of G, this quasi-simple subgroup, and also I want that my quasi-simple group modulo at center is not isomorphic to the alternating group, because that's already being done, then either G has a regular orbit on V, or the pair G and V is one of a finite list of pairs. Okay, so this kind of feeds back into the whole Liebeck-Seitz theorem that Joanna mentioned. Maybe you might be wondering what this finite list of pairs is. Well, here it is. I don't have quite a nice table like Joanna, but it is a nicely formatted table nonetheless, if I do say so myself. So if you have your favorite almost quasi-simple group, you can of course come to this table and see if it appears. And if it does appear, then I can tell you what the base size is, and it's greater than 1, and it appears here. And if it doesn't appear, then that means that there's a regular orbit of your group G on your module V. Okay? I've very nicely, at the suggestion of Martin, had a look at this table and got some sort of bits of takeaway wisdom that you can get, which might be a bit nicer for you to digest. One of the following holds, all of the following holds actually. If you've got a module that's of dimension greater than 24, or the size of your vector space is larger than 27 to the power of 8, then G has a regular orbit on V. Okay? Now, the next piece of information kind of goes back to this bound that Joanna had up here, this lower bound here. So certainly, the base size for a group has to be at least the ceiling of this ratio of logs here. So the second bit of information I can tell you is that actually an upper bound for the base size is this ceiling plus 2. Okay? So there's not a lot of wriggle room there. And finally, the base size for all these groups is at most 5. Okay? Yeah. So I want to talk a little bit about how we go about proving such a result. And the techniques I use are somewhat different to Joanna's. So clearly the first step we should take is to check that we can actually have a regular orbit in the sense that the vector space is large enough to contain a regular orbit. So of course I first check that my vector space is larger than the size of my group. Then my technique relies on these fixed point spaces. Well, a fixed point space is exactly what you would expect it to be. It's just the one eigenspace of your group element on your vector space there. So if G has no regular orbit on V, okay, then that means that there's no vector in V with trivial stabilizer. So every vector has to lie in the fixed point space of some non-trivial element of your group. Okay? So we can write V as the union of these fixed point spaces here. Now, if you think about the elements of a group, if you have an element of composite order, you can always take a power of it that's of prime order. Okay? That's pretty trivial. But in particular, that prime order element will contain, its fixed point space will contain the fixed point space of any element of composite order that you can power up to get there. Okay? So actually, instead of considering all of the elements of our group here, we can consider elements of prime order. But we get into a bit of trouble as well, because sometimes you can power up your group element to an element of prime order, but that element lies in the center of your group. Okay? And so that's not super helpful. So here we also have to consider what I call elements of projective prime order, which means that the coset, if you take the quotient group with the center, so you mod out the center, then when you send the group element over to the quotient group, then that coset has prime order. Okay? So we have to consider not only prime order elements, but also these projectively prime order elements. Okay? So now, since this holds, then in particular, since our fixed point spaces are probably going to overlap in some way, then if G has no regular orbit on V, then the size of V has to be less than the sum of the sizes of all these fixed point spaces. Okay? Now, the size of a fixed point space is constant across a conjugacy class because you're just moving the fixed point space around. So we can basically just consider one representative from each conjugacy class of elements of projective prime order and figure out the size of the fixed point space there. Okay? Now, since we're working with almost quasi-simple groups, and in particular the groups that I care about are groups of Lie type, we know a lot about their conjugacy classes. Okay? So really the crux of this approach, if we're going to do a proof by contradiction here, is to somehow find upper bounds for this size of these fixed point spaces. Okay? Now I'm going to illustrate a few approaches of how we do this through a number of examples. So the first one, which I believe that David Craven had in his talk, is PSL45 acting on this 248-dimensional vector space over GF4. Okay? So how are we going to bound the fixed point space here? Well, Joanna alluded to this technique in her talk, but we use some generation result for this PSL45. So Goralnik and Saxel have a nice paper from 2003 where they talk about, okay, suppose you've got an almost simple group, and you take some element of your almost simple group, how many conjugates of that element do you need to generate the simple group, the group generated by the simple group, and whatever that element is, just in case it's an outer order morphism or something like that. Okay? So from their work, we know that at most 4 elements, 4 conjugates of an element of prime order generate PSL45. And then through a result of GRAW02 and Tiepp, they show that the dimension of your fixed point space is at most, so here it would be 3/4, but in general if it's generated by k conjugates, then you have k minus 1 over k here, times the dimension of your vector space. Now notice this doesn't depend on the actual module you take, this only depends on the group, okay? Now because this module is so large, it's 248 dimensions, we then just go back to that proof by contradiction I had on the last slide, okay? So if there's no regular orbit, then this should hold, and if you plug that into Mathematica or your favorite calculator, then you'll see that this is actually a contradiction, so there's a regular orbit, okay? So we call this sort of the crude technique, because somehow we're not analyzing individual classes of elements of prime order, we're just kind of taking some upper bound for all of the fixed point spaces, okay? But it turns out that this approach is extremely effective, and it gets rid of most of the groups and modules that I have to consider, and so I'm just left with a finite list that I have to go through. So in those cases, we have to work a bit harder. So here's my next example. I've got 2.f4 of 2 acting on this 52-dimensional space over GF3, okay? So fortunately for us, for this group, and a lot of the time with the groups we have left over, the Brouwer characters are available, okay? So I can take my projective prime order elements that doesn't have 3 dividing their order, I can just look up the character, determine the eigenspaces directly, and that's what I do for those elements. Of course, we're left with the elements of order 3, or projective prime order 3, and here we try a number of approaches to bound the fixed point space. So the first is to use this GRAW02 and Saxel / GRAW02 and Tiepp result again. So it might be that once we are only left with the elements of projective prime order 3 there, we can use those results, and the bounds for these other elements are better, and somehow we get this contradiction and everybody's happy. Sometimes, because GRAW02 and Saxel just give upper bounds that work for all of the prime order elements in the group, it might be the case that a fewer number of conjugates are required to generate the whole group. So we can use GAP to try and find, say, 3 conjugates of an element of PSL45 that generate the group, for example, and that gives us a smaller bound, okay? Hopefully that works. If that doesn't work, then we try to construct the module directly in GAP, hopefully if the module's relatively small, and then either by finding the conjugacy classes or taking elements at random, we can find elements of projective prime order 3, okay? And then it's pretty easy to find out the dimension of the fixed point space there. Or as a last resort, because it's much more complicated, we can drop down to some sort of maximal subgroup that contains our favorite elements of projective prime order 3, look at the action of that group on the composition factors of this module, and then say something about the fixed point space there, okay? In any case, all of these approaches require us to actually split up this sum here according to conjugacy classes. So we can't just plug in the whole size of the group and hope for the best, okay? Right, so that's quite a slightly trickier example, and in fact most of the remaining groups and modules that I have fit into sort of this general form, okay? There were a couple of examples that were extremely tricky, so this is one of them. So now I'm taking my group to be 2.G2 of 4, acting on a 12-dimensional vector space over GF7, okay? Now, unfortunately for us, the number of 2B involutions is 4095, which is larger than 7 to the 4, and each of these has an 8-dimensional fixed point space, okay? So if I take the size of my conjugacy class and multiply by the size of the fixed point space. That's already larger than the size of the vector space, right? So that's bad. And we can't use this method to show that there's a regular orbit. Fortunately for me, Eamon O'Brien and Jürgen Muller were very generous in helping me resolve such cases. So here I believe that Jürgen used the OR packaging gap to find that there was no regular orbit, but this case was left open for a few months, so it was highly non-trivial to solve. And I really want to take this opportunity to thank Eamon and Jürgen for their help in resolving these cases, because I don't know what I would have done without them. All right, so I've given you some examples for the cross-characteristic case now, and I hope you've got a reasonably good idea about the techniques that I've used. And I want to just finish by talking about the defining characteristic case. So this is very much work in progress, but I'm sort of getting towards having a result, so I'll just share the work with you. So firstly, I'm going to talk about when you've got an almost quasi-simple group. Same deal, the restriction to the quasi-simple normal subgroup is absolutely irreducible. But here I want to, when I take my quasi-simple group and one out by the center, I get PSL and Q, okay? So if I'm in this case, then one of the following holds. Well, first of all, either G has a regular orbit on V, or V is one of these 6 very well studied irreducible modules for G, or they're duals. And sometimes these representations can also be realized over a subfield, so I include those there. Okay, and this sort of feeds back into this bit here of the Hall-Liebeck-Seitz theorem. Okay, or part 3 is that you have G and V being one of 5 small pairs where the base size is equal to 2. Okay, so this is, the usual thing where you've got like a smallish group and the numbers don't quite work out. So for example, I think if you've got PSL 7 of Q acting on the wedge cubed, then there's no regular orbit there. Okay. All right, so that's for linear groups. What about the other groups of Lie type? Well, I'm not even going to call this a theorem. I'm going to call this work in progress, because I've still got a few cases to do. But here it looks like we have a very similar result happening. So either G has a regular orbit on V, or V is the adjoint module for G, and the base size is equal to 2, or you can't have a regular orbit in the first place. So here, this is kind of trivial when we're just looking for a regular orbit, because it just says that the group is large, the size of the group is larger than the size of the vector space, so you can't possibly have a regular orbit. Or we've got G and V being one of 6 small cases that I'm yet to have finished off. Okay, so hopefully within the next little while I would have finished this off. So in the cross-characteristic case, I had this nice, nice corollary that had this sort of takeaway information that you could write on the back of an envelope. So do I have a similar thing here? Well, of course, I can't tell you for sure because I haven't quite finished off these cases yet, but here's what I suspect it will be. So I suspect it will be that if the FQ, FQ is the field associated to our group, okay, our group of Lie type. If the FQ dimension of our vector space is, well, I think this should be strictly larger actually, than the dimension of G plus 1, then I think that G will have a regular orbit on V. But I've still got a few cases to resolve. Now here, in defining characteristic, the approach is very different. So we have a lot of literature about irreducible representations in defining characteristic. So we use a very different approach that was pioneered by GRAW02 and Lawther, where they take the irreducible representation in the algebraic group, and you can talk about the weights of such a representation, and then they somehow take define equivalence relations on these weights and use those equivalence relations to give you an upper bound on the size of a fixed point space. Okay. All right. I think that's all I wanted to say. Thank you.
Questions? There's going to be a quiz on the slide of all the tiny numbers. I hope you paid attention. If you're getting wine, you're going to have to get the lines right.
I mean, they're relatively small. I think the ones that I have left rank at most 9, so relatively small, smallish.